Okay, as I mentioned on Wednesday, today's class we're going to be talking about digital to analog conversion. What I want to tell you right now here is there are some pictures and even a small video of showing what you should be doing with the PSOC device. You're going to need to hook it up to a potentiometer. I used a 100 kilo ohm potentiometer, and I just went ahead and just put it in a breadboard. And then if you look at the picture here, the yellow wire is at the kind of the top of the potentiometer, if you look at my picture, and that's actually being connected to the 3.3 volt external. Then the orange wire, which is at the bottom, is then attached to a ground pin. It doesn't matter which ground pin, it just has the ground there. Then the red wire is attached to the pin that is designated as port 0, pin 0. Technically, you don't have to use port 0, pin 0. You can use any of the other ports as well. It's just important when you do your pins that you label the ports correctly and you assign the pins to the correct location. Alright, so now let's go ahead and get started on our actual project here. So we'll go File, New Project, like we always do. I did use this last, but if you want to double check and make sure, we're going to do a PSOC4600. Of course, empty schematic as always. So we'll call this here analog to digital. And you'll see there, I don't like putting spaces in it. Some software, PSOC's fine with spaces, but some software out there is not okay with spaces. Let me dismiss that email. And so I'll just call it design 1, that's fine. So we're going to finish. So we have our empty schematic here. What we need though is what we're going to, well, let me tell you what we're going to do is we're going to use this potentiometer, as you can see in the video, to control the brightness of the blue LED. So we're going to make it so that when I turn the knob on the potentiometer, the LED gets brighter or dimmer, so on and so on. And it's actually kind of a cool thing because it's something, you can build a circuit that does the same thing, but here we're using and programming a chip to do the PWM stuff for us. But because of this potentiometer, we're going to be reading in an analog voltage from 0 up to 3.3 volts. And I'm going to show that also when we get into the debug mode on how that works. But let's go ahead and get started. So that's what we're going to do. So first off, we know we're going to need some pins here. I'm going to need a digital output pin because that's going to be my LED. So I will call this my B LED. Click OK on that because it's direct drive and everything. And then I need an analog pin. Drag analog pin over, and I'm going to call my analog pin. Technically, you can call it whatever you want. We're actually not going to need to call this pin ever, but I'm calling it pot in for potentiometer input. But it is an analog. And first off, let's even notice here. Notice that you have a green wire here and a red wire here. And that's basically just to indicate the difference between digital and analog. So this is an analog signal coming. Now, this microprocessor is a digital device. So we have to, in order to read analog signals, you have to do analog to digital conversion. Now, it's ADC, but if you want to get to it from the main menu, here you can see analog and then ADC. There's also digital to analog if you want to output analog kinds of things. And then there's only one option here, and so we're going to choose this option, and we're going to drag it in here. Now, a lot of this we're not actually going to use here, so let's go ahead and double click on it here. So first off, we've got this channel sampling rate and clock frequency. We'll have to change some of this here. The sample mode, there's two ways you can have this free running in hardware. We're going to run it in free running mode, which means it just is, once we tell it to start doing conversions, it's just going to constantly be doing conversions. So it's always going to be looking at the analog pin and always doing the digital conversion. You can do it where if you're only wanting to look at it like once and every so often, you can do what's called a hardware trigger. And then where a clock source is internal, but you could also have an external clock as well. Now, the input range here, we have to be careful in what we tell. It's like right now, it's set as an internal 1.024 volts. So if you see here, the single-ended mode, which is what we're going to run this in, it's going to be run in single-end mode, we can read in voltages from 0 to 1.024. But I want to be able to read in voltages from 0 to 3.3. So I need to change this, and you just change it to VDDA. And then you can see, hey, it's gone from 0 to 3.3 volts. So we've got definitely what we want here, but now we've got this exclamation point. It says clock frequency must between 1 megahertz and 9 megahertz. So select the clock frequency and just make it between, because right now it's set at 12 megahertz. So I just went ahead and set it down at 1 megahertz. You could use 9, it doesn't really matter. This is actually just how fast it's going to be sampling the analog input to turn it into a digital signal. Then the next thing we need to go here, well, I'm going to click OK. We're going to go back into there a second. Right now, this is set up to actually read in 4 analog signals. And you could set 4 analog signals, and it's set in a differential mode, meaning that you have an analog input and you're going to be comparing it to some reference value. So we're going to want to not do it in this differential mode range. We're going to want to do it in single end. So we go 0 to 3.3, because basically in the differential you can do the comparison Vn to plus or minus 3.3 volts. So channels here, first off, we only need 1 channel, so I'm going to just go down to 1 channel here so that we only have 1 here, and I'm going to change this from differential mode to single mode. And then we've got different clocks we can use and acquisition times. That's some more advanced features that we're not really going to get into in this course. This is all we need to do, and we click OK. And then we can see this has changed quite a bit, and you can see the minus here is going to VSS, which VSS is ground. So it's going to be comparing whatever's on the input to ground. So that's why it's going to be 0 to 3.3 volts. Alright, so then all we need to do for the analog here is wire this bad boy up. And then we still need to create the PWM here for us. So the PWM that we need to create here, well, it's just the regular PWM. So I'm going to get my PWM in here. And I'm going to call this, PWM-B for blue. I'm going to leave it in 8-bit mode. 1 output, I don't need it, and I'm just going to leave it the period at 255 and the compare value at 127 to start with. That's fine, and then I'm going to just hit OK. But then remember, we need to have a clock signal for this PWM, so I need to put in a clock, and it's set at 12 megahertz. You could change the frequency to be lower. I mean, it doesn't need 100 kilohertz would be fine. I'm just going to leave it at 12 megahertz. It doesn't really matter. And then I need to connect up my PWM to the blue LED. Now, before we generate the API or assign pins, I want to look at the data sheet for this A to D analog to digital conversion. So I'm going to pull up my data sheet here. And I had already opened it because I've been working on this before I made the video. And I'm going to go to the application program interface, the APIs, and I'm going to go look at the functions. Notice that there's also things like global variables, usable constants, macros, and all sorts of other things. But we're really interested in the functions. Okay, so notice here there's this A to D start, performs all required initialization for the component, enables the power. Power is set to the appropriate power based on the clock frequency. Okay, so obviously we're going to have to start it. Initialize we're not actually going to have to use, but that would be something we could do. So then we say start convert. It says for free running mode, this API starts the conversion process and it runs continuously. In trigger mode, this routine triggers every conversion. So if we're in triggered mode, remember we had that hardware triggered mode, this would be where we would use this function to take a single reading. But we're in free running mode, so we're going to execute this command. I keep hitting that, I don't want to click on that. We're going to execute this start convert command once, and that's going to make it so that this is constantly doing conversions of analog to digital. But now that's not all we have to look at here. Look at here, there's this get result underscore A to Z get result 6T, and this gets the data available in the result register. So remember, just because it's converting doesn't mean we have that data stored yet. We need to actually get that data and store it in a variable. So that's where that get result command comes in. There's also a lot of other things you can look here, but there's also some other things, because that get result is going to be a 16-bit integer, and we'll look at it. It's going to be a count. The way these A to DC analog to digital converters works is they basically do a count, and you take that count then and convert it to a voltage. Now we could try and do that conversion in our hand and write an equation for it, but what's nice is it's got this already built in. You look here, ADC counts to volts. We could even do counts to millivolts or even counts to microvolts. So let's go ahead and look at some of how these work here. So we've got A to Z start. I'm going to zoom in here a little bit. This performs all the, okay, so this is, we're going to start up the thing just like we would before, and then the convert, well, that's a void function, so that's just going to start a conversion. And then let's see here with the get result. Okay, what returns a 16-bit integer, so we're going to want to have a 16-bit integer for that. It expects an unsigned integer 32, and it's wanting the channel. It says get the data available in the channel result register. Channel, the ADC channel to write the result from. The first channel is 0, which would make sense because we're programming and it's already been like that before. So we're going to have to do int an integer to store the value, and we're going to do A to C get result 16 channel 0. That's what we're going to have to do. Then if we scroll down a little bit more, counts to volts, it needs both the channel and the actual A to C counts, and then it returns a floating point number. So basically we're going to need to put in the channel again, which is 0, and then that count we got from the get results we're going to have to put in order to convert that to a float. Okay, so then what are we going to do here? Well, I want to go back to the PSOC program, and I do want to set up my pins here before I generate my application. So my blue LED, I believe, is pin 27, and then we put the pot, when I connected it, and if you see in my pictures, I connected it to port 0 pin 0, which is pin 24. Now if you connected it to a different port or different pin, that's fine. As I said, you don't have to do port 0 pin 0, but that's the one I did. You could have done port 0 pin 1, so on and so on. You could have picked a port over here. There's lots of ones you could have done, but I just picked port 0 pin 0. Now we are ready to generate the application. So we generate my application. And I like being on my computer at home because it's already done generating the application, and we're ready to write the code here. So we go in here and write code. But before we do that, I'm actually going to stop this video, and then I'm going to make a video that's just talking about the code.